Hello, my name is Antonella Ruta. This presentation will be discussing my MEng project, a preliminary investigation of a hydrogen injection wedge strut for a Scramjet combustor application. This investigation seeks to model the effects of viscosity, turbulence, and combustion on the flow field of a wedge strut injection combustor by means of ANSYS Fluent. With the effects of viscosity implemented in the model, boundary layers should form along solid walls, and a free shear layer, or mixing layer, should also form around a hydrogen injection stream due to the difference in velocity from the bulk flow to the hydrogen stream. This causes friction between the fluid layers and between the fluid layers and solid boundaries. The effects of turbulence should occur behind the wedge base, which is normal to the main flow, since an adverse pressure gradient is expected, generating a wake region. With the injection of hydrogen, recirculation region should form, and the change in turbulent effects are compared with the implementation of a combustion model. The combustor performance can be evaluated by mixing efficiency, combustion efficiency, and total pressure loss. These parameters are heavily influenced by formation of strength of shock waves, as well as the dissipation of turbulent eddies within the combustion zone. The model used in this investigation is proposed by W. Weidmann from the German Aerospace Center, DLR, which is used as the base model in several published articles investigating similar criteria due to its good flame-holding capability. The original model by Weidmann consists of 15 hydrogen injection ports. However, for simplicity of this investigation and a lesser computational cost, a 2D model suffices. After running an initial viscid simulation with hydrogen injection, the geometry is divided into several regions for mesh refinement, where the pink, orange, and green zones have the smallest grid sizing, and the yellow and cyan regions have slightly larger grid sizing, while still maintaining an average Y plus value of around 1, where the Y plus value is a non-dimensional distance from the wall to the first mesh node and is ideally around 1 to capture boundary layer effects near the walls. This is also achieved by adding mesh inflation along the combustor and strut walls, which is important in viscid models with no slip conditions. Also, inflation is applied to lines A, B, and C, where flow properties are expected to change. There are 4 cases simulated in this investigation, where case 1 is inviscid with no hydrogen injection, case 2 is viscid with no hydrogen injection, case 3 is viscid with hydrogen injection, and case 4 is also viscid with hydrogen injection with the addition of a combustion model. A one-step reaction mechanism is selected which produces water vapor from the hydrogen and oxygen reaction. Prior to analyzing results, it must be ensured that the mesh quality is not influencing the results, i.e. if the mesh is too coarse, therefore not providing enough precision. 3 mesh refinements were tested: a coarse mesh with over 126,000 nodes, a medium mesh with 166,000 nodes, a fine mesh with 240,000 nodes. The grid independence is evaluated by static pressure distribution along the combustor centerline and bottom wall, as well as the hydrogen mass fraction and turbulent kinetic energy contours. At a distance of 190 mm, the fine mesh center static pressure deviates slightly higher, and beyond 210 mm, the coarse mesh center static pressure deviates lower than the fine mesh value by a maximum of 2.78%. The bottom wall static pressure of the coarse mesh deviates lower beyond a distance of 240 mm, with a maximum deviation of 4.47% below that of the fine mesh. Also, both coarse and medium meshes result in a greater static pressure along the bottom wall between 130 and 142 mm. This can be due to early prediction of expansion of shock waves, which propagate further downstream. Additionally, the coarse and medium meshes fail to capture the high magnitude of turbulent kinetic energy regions behind the strut and have some discrepancies with hydrogen mass fraction, though there isn't much variation between the medium and fine meshes, especially when compared to the coarse. Thus, the fine mesh is a reasonable level of refinement for this investigation and is selected to proceed with. Additionally, the density contours of the non-combusting and combusting case with the fine mesh is compared against the Schlieren images, or shadow graphs, from a physical flow experiment with the strut proposed by Weidmann. Several flow features, including initial shock and expansion waves and their reflections, as well as shear layers around the hydrogen stream, are present in both sets of results, as well as simulation results from other published articles, making the simulation setup and boundary conditions used in this investigation a reasonable choice. The boundary conditions used are that of Weidmann's original experiment, where both air and hydrogen inlets are at atmospheric pressure, with air entering the combustor at Mach 2 and 340 Kelvin, and hydrogen at Mach 1 and 250 Kelvin. The mass fraction of air is 0.232 oxygen, 0.032 hydrogen, where the remainder is 0.736 nitrogen fraction, is inert, therefore not influencing the species' interactions. The inlets are set as pressure far field, which is suitable for sonic and supersonic flows, modeled at free stream with static conditions specified, which are the pressure and temperature. Having these known, constant initial conditions are known as Dirichlet boundary conditions. The outlet is set to a pressure outlet, which interpolates information across each grid cell, starting from the inlets, to determine flow properties of the combustor outlet. This is known as a Newman boundary condition. A no-slip condition is applied to all solid walls, inclusive of combustor top and bottom walls, and all strut sides and base. The no-slip condition specifies that fluid layers adjacent to the walls are of zero velocity, both parallel and normal to the surface. This is applicable in the viscous models, cases 2, 3, and 4, which should induce velocity in thermal boundary layers. The walls also do not permit heat transfer or movement of particles through them, thus making the control volume only the interior flow. Cases 1 and 2 with no hydrogen injection were simulated with the density-based transient solver, whereas cases 3 and 4 with hydrogen injection and with combustion were simulated with a pressure-based steady-state solver. The shear stress transport, or SST, K-omega turbulence model was applied to all viscid cases. The injection of hydrogen species in cases 3 and 4 were modeled with the species transport, and the combustion model in case 4 is the eddy dissipation model. The SST, K-omega, and eddy dissipation models have been used in several published articles, where the SST, K-omega model in particular has been suggested in a comparative investigation with other turbulence models for this specific Wedge Strut combustor case. All cases were initialized from the air inlet and had residuals converge to the order of 10 to the -5 and -6, which is consistent with published literature. Additionally, the continuity residuals have converged to a reasonable precision, indicating meaningful results are produced. Firstly, an oblique shock of 35.24 degrees, calculated by one-dimensional oblique shock relations, is achieved at the 6-degree half-angle wedge tip for all cases. This induces a sudden decrease in Mach number across the shock, which is an irreversible process. In cases 1, 2, and 3, an expansion wave from each of the strut base corners is present, where the strongest expansion wave is in the inviscid case and the weakest is in the case with hydrogen injection. This is because the central wake region in the inviscid case does not have a shear layer around the central wake region, so the flow must turn more from the strut sides toward the centerline. Case 2 considers viscous forces, so a shear layer exists graduating the subsonic central wake region to the supersonic main flow. The expansion wave from the strut base only turns to meet this border. In case 3, the central subsonic region is even larger since the hydrogen injection stream is displacing it near the strut base, and a longer recirculation region is generated, which will be discussed in a later slide. Case 4 does not produce an expansion fan at the strut base, since the subsonic turbulence region is wide and it actually produces a shear layer that is greater than the 6-degree half angle of the strut, which instead generates a shock at each strut base corner. In case 1, 2, and 3, the initial reflected shock interacts with the expansion wave, decreasing the strength of both. So the Mach number across the expansion wave does not increase as much, and the Mach number across the shock wave does not decrease as much as it did prior to the interaction. This is known as destructive interference. However, since the expansion waves are still traveling in an expanding area, they regain some strength, increasing the Mach number again as it approaches the top and bottom walls. Since the top wall is angled to expand the combustor area, the flow is directed slightly upward, such that it follows the path from the center of the strut base to the center of the combustor outlet. There are also several shock reflections when the expansion waves hit the top or bottom walls and the central shear layer around the wake region. The presence of boundary layers in cases 2, 3, and 4 lessen the distance of reflections can travel, preserving their energy, allowing less of a delta in flow accelerations across each expansion from the last. A direct comparison can be made between cases 1 and 2, since both have no hydrogen injection, where an extra shock reflection occurs in case 2 near the outlet, accelerating the flow to around Mach 2.15, whereas the inviscid case has an exit Mach of under 2.1 in the peripheries around the central wake region. Here, the contours of static pressure are presented. Since there is a sudden decrease in area due to the angled strut, static properties transmitting to adjacent air molecules faster than the speed of sound are met with a sudden gradient in gas properties, inducing a non-isentropic shock wave where the static pressure must increase. Following the initial shock reflections on the top and bottom walls, the static pressure must increase further, creating these large high-pressure regions indicated by the red patches. The lower pressure bands downstream the strut located where the expansion waves occur decrease in static pressure nearing the most downstream part of the expansion wave. This is because the expansion waves are comprised of a series of Mach waves which successively accelerate flow and decrease static properties. The additional shock reflections in case 2 and 3 create a pressure decrease in the correlated regions. Due to the oscillating size of the combustion region in case 4, the static pressure increases and decreases with the shock and expansion interaction with the central shear layer. Since the waves travel a shorter distance between the central region and combustor walls than in other cases, the waves are weaker, so less abrupt pressure gradients occur. Similar to the static pressure pattern along the expansion waves and shock reflections, static temperature decreases in the same regions. The central regions in cases 1 and 2 with no hydrogen injection have a significantly high temperature since the Mach number has turned subsonic from the free stream because kinetic energy has converted to potential energy, increasing static temperature, allowing enthalpy to maintain constant. The thermal boundary layer along the top and bottom walls are very evident in the viscid cases compared to case 1, especially in case 3 since expansion waves are stronger. The thermal boundary layer increases in thickness and magnitude of static temperature when a strong expansion wave strikes the adiabatic wall. A thermal shear layer is especially evident in case 4, where its high temperature is suitable for autoignition at 858.15 Kelvin, which is prior to the core flow within the shear layer that begins at 145 millimeters. The turbulence effects in case 2 are due to the adverse pressure gradient influencing a negative velocity, which creates a recirculation region behind the strut. The pattern is fairly symmetric since the top wall has only just begun to angle upward. The turbulent kinetic energy begins to turn upward downstream as the wall continues to angle. In case 3, the hydrogen injection stream parts the turbulent region into 2 more distinct recirculation regions than present in case 2. Additionally, these regions have higher turbulent kinetic energy, as seen by the color bar, because the sonic hydrogen stream transfers more rotational kinetic energy to the air behind the strut as it passes by. Thus, less energy is devoted to stretching these turbulent regions more downstream. Since case 4 applies the eddy dissipation model, large turbulent structures slowly dissipate into smaller eddies until hydrogen and oxygen molecules interact and rapidly combust. Because of this, magnitude of turbulent kinetic energy is lower than cases 2 and 3, allowing more energy to be used to carry the eddies downstream. Turbulent kinetic energy contours are comparable to the hydrogen mass fractions. The high-energy initial hydrogen stream that separated the 2 recirculation regions in case 3 can be seen here. It is more streamlined than the combustion model in case 4, where the small dispersed eddies are more influenced by the expansion area in the combustor and flow slightly upward, including more concentrated regions of the hydrogen stream. The mole fraction of water vapor is also pictured below, where the region of little to no water vapor is where the hydrogen is present. Note the similar contour shapes. The presence of water vapor is a sign that the combustion is or has occurred, since it's a product of the one-step reaction between hydrogen and oxygen. Cases 1, 2, and 3, fluctuations in all flow properties occur in the inviscid case, since expansion waves and shock reflections must travel further with the absence of boundary and shear layers. The first increase in pressure, temperature, and density, and decrease in velocity occurs downstream the reflection of the initial oblique shock off the central shear layers following its previous reflection off the combustor walls. The first inverse trend of this occurs when the low-pressure regions from the expansion fans join at the centerline, creating the shock diamond. The shock reflection after the expansion wave intersection with the shear layer creates the next high-pressure, high-temperature, high-density, low-velocity region. This pattern repeats until the combustor outlet, but diminishes with each successive shock-shear layer interaction as the waves lose kinetic energy. In case 4, the initial static pressure behind the strut is much higher due to the absence of the expansion fans and a more consistent density from a more uniform dissipation of eddies to create a homogeneous mixture. The density is also relatively constant because the central flow remains subsonic and is less prone to compressibility effects. The small drop in density at 190 millimeters is when the central flow approaches Mach 1. The static pressure plateau and downturn and velocity plateau and upturn at 257 millimeters is indicative of a plateau in combustion efficiency, which will be presented in a later slide. The centerline static temperature reaches the auto-ignition point at approximately 145 millimeters, which correlates to a sudden increase in centerline velocity at this distance. Conversely, This reduces static pressure. Peaks and troughs in the flow properties along the bottom wall occur for the same reason as they did along the centerline, so we will instead move on to the obvious discrepancies between the cases. The high pressure spike in case 4 is due to the 2 oblique shock interactions at the wall, whereas the other cases only have 1 oblique shock. The wavering increase to a plateau in static pressure is due to the relatively weak shock reflections between the center shear layers and the walls. The inviscid case has a lower wall temperature because no thermal boundary layer gradient exists, and all viscid cases have zero velocity, unlike case 1, because of the no-slip condition. Reynolds number and boundary layer thickness are inversely proportional. Note that viscosity, density, and velocity are also factors, where the spikes in boundary layer thickness or dips in Reynolds number occurring during a shockwave boundary layer interaction on the wall. This is because the downstream of shock, velocity is reduced and a less steep gradient is needed to transition from the zero velocity wall to the slow flow. The consistently weak shock train in case 4 combustor peripheries creates a more constant boundary layer thickness than the other cases. Here, the cross-sectional velocities throughout the combustor indicate a non-zero velocity at the walls for the inviscid case, while velocity approaches zero at the walls for the viscid cases. Also, the absence of a shear layer around the central region in case 1 allows the velocity to reach a lower speed than its viscid counterpart in case 2, which has a smoother gradient from the upper and lower regions of the combustor toward the central wake region. As previously discussed, for case 4, the velocity begins to increase around 36 millimeters downstream of the strut until 100 millimeters downstream, before decreasing until 148 millimeters, then steadily increasing again to yield the largest exit velocity of all cases, aiding in thrust production. Mixing efficiency is the ratio of hydrogen mass flux available for combustion to the total mass flux of injected hydrogen. The equivalence ratio is compared to the ideal ratio of 0.136 from the original experiment. Since the eddy dissipation model has a gradual transition from larger recirculation to small-scale eddies, the mixing propagates further downstream and is reached at a further distance of 247 millimeters than in case 3, which occurs at 224 millimeters. The flow properties are averaged across sections spaced 10 millimeters apart from the strut base to the combustor outlet. Since cross-section density is fairly constant throughout the combustor in case 4, the initial increase in efficiency is due to the drop in velocity, while the following decrease is from the spike in velocity after auto-ignition in the wide central region. The final increase to the plateau is mostly due to the reduction in hydrogen mass fraction, since the velocity is fairly constant beyond 257 millimeters. It reaches a combustion efficiency of 73.42%. Since flow across a shockwave is adiabatic, meaning stagnation temperature remains constant, and the process is both irreversible and non-isentropic, the total pressure must decrease, as entropy is a function of change in total pressure over total density and total temperature. Entropy also increases with boundary layer separation, further reducing total pressure. In case 4, nearly half the combustor area is utilized by the combustion zone, which severely limits the main flow's ability to maintain free stream conditions, especially through the strong shock trains. By eliminating the combustion zone from the cross-section averages, the total pressure loss reduces its magnitude, though has a smaller trend, as indicated by the dashed line. Overall, the combustion has a total pressure loss of 46%. Results obtained in this investigation using the SST, K-omega turbulence, and eddy dissipation combustion models are comparable to published data. Velocity and thermal boundary layers, as a product of viscous forces between fluid and solid boundaries, and shear mixing layers develop around subsonic wake regions. In the combustion case, complete mixing occurs at 245 millimeters and combustion efficiency of 73.42%. Shockwave interactions with boundary layer mixing increases total pressure loss, with case 4 experiencing a loss of 46%. However, this aids in mixing efficiency, which is a trade-off to be further investigated. Since complete mixing occurs before the combustor exit, the potential for reduction in total pressure loss by shortening the combustor can be investigated. Also, residence time analysis can be done to support the results of mixing and combustion efficiencies. Different combustion models and multiple reaction mechanisms instead of this one-step hydrogen-oxygen reaction can be simulated and compared against experimental data. The boundary conditions along the walls can also be refined to include friction, partial slip, and heat exchange, which may affect boundary layer growth and thus the internal flow field. Once a 2D model is established to match physical data more closely, it can be applied to a 3D simulation. Thank you very much for listening to my MEng presentation. I appreciate your attention.